Te toto o te tangata he kai. Te oranga o te tangata he whenua. While food provides the blood in our veins, our health is drawn from the land. Between oil spills setting the ocean on fire and unprecedented floods displacing hundreds of thousands of people from their homes, it's evident that we're neglecting our land, and the effects of climate change are a fast approaching reality. We don't need to look far to realise that this is one of our most pressing issues, and the cause? An increase in greenhouse gases produced by a growing population with a growing need for consumption. As you can see, world population growth has increased exponentially, with this figure predicted to reach 9.7 billion people by 2050, and a 50% growth in total energy consumption. So how does this climate change process actually work? Well, when the sun emits electromagnetic radiation, some of this intensity arrives at our atmosphere. A proportion of this energy is absorbed by the Earth, warming it, while the rest, primarily infrared, is transmitted back into space. Greenhouse gases such as carbon dioxide and methane trap this heat in our atmosphere, before then transmitting it back towards the Earth, causing our planet's temperature to rise even further. But it doesn't stop there. This has a number of destructive consequences. More droughts, deadly heat waves, rising sea levels, loss of biodiversity, and the list goes on. So where do these gases come from? Looking to statistics published by the Ministry for the Environment on greenhouse gas emissions by sector, in 2019, 48.1% of our gross emissions were attributed to agriculture, and 41.6% to energy production. Agriculture and the dairy industry in particular, while harmful to our environment, is inevitably one of the most crucial contributors to our economy. It's not something we can drastically change, and we have already made efforts to reduce its environmental impact. In fact, analysis by Ag Research shows that New Zealand farmers actually have the world's lowest carbon footprint, with 46% less than the average of international producers. Instead, you will have noticed that most of the solutions proposed to combat climate change are energy focused. In order to reduce our quantity of global energy consumed, it is essential to pursue renewable energy sources such as wind, hydropower, and solar. However, from projections for 2050 by the International Energy Outlook, while renewable sources look to be the most consumed type of primary energy, they only comprise 28%, leaving 72% to existing harmful sources, including coal and fossil fuels. This is because transitions take time, and our demand for energy is accelerating at a greater rate than our innovation processes can keep up with. They're also relatively expensive to implement. Let's say even if we could theoretically switch to 100% renewable energy, this would require immense infrastructure. For example, New Zealand's proposed $4 billion hydro storage plant, which excludes the cost of any environmental damage for its construction. Moreover, it doesn't undo any of the existing harms we've already caused to our planet, which is said to be irreparable by 2030. But imagine, if we could solve two problems at the same time, create a better renewable energy solution, and reverse the greenhouse gas effect. Well, we can, since thermoelectric materials look to do just that, by converting excess heat energy into electricity. This embodies the tikanga Māori concept of kaitiakitanga, which refers to the sense of responsibility to care for and preserve the natural environment and its resources for future generations, following the idea that humans and nature are related parts of a unified whole. Now, thermoelectrics aren't a new concept, and they can be explained through something called the Seebeck effect. A traditional thermoelectric system looks just like this, with two dissimilar electrical conductors connected in a circuit, typically metals. The N-type conductor has an excess of electrons, while the P-type has holes that accept electrons. When heat's applied to one side of the conductors, this energizes the electrons, giving them more kinetic energy to move, and establishes a temperature gradient where one side of the conductor is relatively hot while the other is relatively cool. These electrons transport energy by flowing from the warmer end to the cooler end, which can then be harvested by connecting the circuit to an external source. In the past, however, thermoelectric generators have been too large and often incurred unrealistic costs to manufacture, so they've never really taken off. This is where spin coating comes in, a technique used to apply uniform thin films to a surface. By rapidly spinning an object, this creates a centrifugal and outward circular force, which when a small amount of a coating material is deposited onto its surface, evenly and thinly distributes the substance, as shown here. Research conducted by the King Abdullah University of Technology has shown that there is a simple and cost-effective method of spin coating a surface in thermoelectric materials, such as lead sulfide quantum dots. A quantum dot refers to a semiconductor particle which is extremely small, being on the nanoscale, that can influence the behavior of electrons. To give you a better idea of what that looks like, the normal typical layer is only 200 nanometers thick, compared to the width of a human hair, which is 75,000 nanometers. The amount of energy that can be generated is dependent upon the particular transport properties of electrons in a given material. So to explain this, we can use a measurement called the mean free path, which refers to the average distance an electron with the given energy would freely travel before being scattered by various other objects within a material. Quantum dot layers resemble a patchwork of tiny crystals with borders known as grain boundaries that separate them from each other. When electrons are traveling and encounter these boundaries, they scatter in various ways. Electrons with longer mean free paths will scatter strongly, like bullets ricocheting off a wall, losing energy, while electrons with shorter mean free paths have higher energy as they're much less affected. According to a 2018 study by MIT, decreasing the average quantum dot size to about 10 nanometers produces 3 times the voltage that the material would have otherwise generated. This is because with smaller dot sizes, the mean free path distance is reduced, as electrons are less likely to scatter, so there's a greater proportion of higher energy electrons. Overall, this spin coating offers us a key advantage. Since the thermoelectric properties are in the quantum dots themselves, they can be applied to a range of different surfaces. And heat's lost almost everywhere. At present, New Zealand's energy production loses around 300 quadrillion joules per year to waste heat, which is half of our total energy consumption. For context, we can examine some of the possible applications. The most feasible example is integrating spin thermoelectrics with photovoltaic PV cells. Solar energy has already been presented as a major opportunity for renewable electricity supply, with declining capital costs. Moreover, there are several national projects scheduled to be constructed, such as the large Pukenui and Lodestone 1 solar farms. One flaw of PV cells is that they only absorb visible light, where thermoelectrics are able to capture a greater portion of the spectrum, specifically infrared radiation. We can create a hybrid photovoltaic thermoelectric system by spin coating the surface of the solar cell with a film of lead sulfide quantum dots. This acts as like a filter, where infrared radiation is absorbed by the thermoelectric layer, allowing visible light to then pass through to the photovoltaic cell, increasing the total amount of energy absorbed. Cars are another example of low efficiency energy usage. Approximately 75% of its energy produced is lost in the exhaust as heat. If only 6% of this exhaust heat could be converted to electrical energy, it would be possible to reduce fuel consumption by about 10%. Thermoelectrics could repurpose this waste energy through spin coating the catalytic converter component of a car, which can then be connected to its battery. The use of spin thermoelectrics in not only cars but other vehicles also mitigates one of their limitations, which is a reduced power output at lower temperatures, since spin coating components can harness the energy from components like the catalyst, which reach temperatures of upwards of 600 degrees Celsius. So, to summarize the impacts, the most obvious benefits are to our taiao, the environment. It's difficult to accurately estimate the reduction in emissions, but predictions based on current technology are at about 3%, which is 2.5 million tonnes. In any case, implementing spin thermoelectrics would improve the efficiency of many processes and thereby reduce the required input of non-renewable sources. Although the retrieval of thermoelectric materials such as lead can lead to some environmental harms, all in all, the relatively small quantity required to form coatings minimizes the quantity extracted and is completely outweighed by the immeasurable costs to the environment from not taking action. Climate change is also deeply intertwined with global patterns of inequality. Our most vulnerable people are disproportionately affected by droughts, among other extreme events, because they increase the scarcity of resources, in turn threatening food and water security. Through a Mātauranga Māori perspective, we can also see that the interconnectedness of the environment and culture is extremely important. The changes that climate change poses to our taiao also threatens our taonga, treasured species, kai, and the ability to manaki in a way that prevents future generations from being able to learn about tikanga, customary protocols. Spin thermoelectrics work to protect these integral aspects to Māori culture and hubs such as marae. On the economic viewpoint, a 2021 study by Stanford University produced the following relationship between the cost per kilowatt of power produced and the payback period for a spin thermoelectric system, which shows that as the temperature gradient increases, the cost decreases to below $10,000 per kilowatt and payback period to about under 10 years. In comparison to geothermal and wind power, which are around $3,000 per kilowatt, the cost is quite high. However, it's important to note that thermoelectrics have no moving parts which require maintenance over time, and we're likely to see the same reduction in costs with increased investment and research. Now, the efficiency of spin thermoelectrics at 24.8% is also very comparable. This doubles that of geothermal power, and the output of a hybrid thermoelectric solar system produces 8 times the quantity of a photovoltaic cell alone. There are countless industrial processes where these could be developed, and there's a clear opportunity for consultation with iwi about their vision of how we can utilise the whenua sustainably to ensure kaitiakitanga is upheld. While New Zealand is a relatively small country, here's our chance to set the precedent, to be a world leader. Mā mua ka kite a muri, mā muri ka ora a mua. Those who lead give sight to those who follow. Those who follow give life to those who lead. This whakatauki exemplifies the importance of international cooperation on this issue, and the codependency of countries to share their knowledge, especially ours of Mātauranga Māori. Thermoelectrics aren't going to single-handedly solve climate change, because we need a diversified range of renewable sources to do that. But what they do is one of the most effective and versatile solutions that we can employ going forward. So let's give them a spin.